Hey guys, welcome to AP Chemistry, Unit 3 from Beyond the 5. Today we're going to be starting off with Chapter 3.1, which is intermolecular forces. So the enduring understanding, which is the main point that the College Board wants us to understand from this chapter, is that intermolecular forces can explain the physical properties of a material. So pretty simple. And so there are three infamous IMFs. And these might be IMFs that you learned in your honors chemistry or regular chemistry class. And these are London dispersion forces, LD, dipole-dipole forces, DD, or hydrogen bonding, HB. And so note, they're intermolecular forces, which are also called interparticle forces, and they're intramolecular forces. And these might be a bit confusing because of the similar spelling, but I'm going to explain the difference. So intermolecular forces are the attractive forces that exist in between molecules or particles, which are weak and the particles are relatively far apart. And so I got this, whenever you see this Faribault, this is from Michael Faribault's video from the College Board, and I really appreciate what the College Board has done for students during COVID-19, but I just wanted to make sure I cited his words, and that'll continue for the rest of this presentation. Anyways, so these are the IMFs that we're talking about. And then there are intramolecular forces, which are the attractive forces that exist within a molecule, which are strong and the particles are relatively close together. For example, a covalent bond is an intramolecular force. And so to further explain this and visualize it really, so this is a water molecule, and between the hydrogen and the oxygen, this is the intramolecular force, the attractive forces that exist within a molecule. And then between these two molecules, these two water molecules, these are intermolecular forces, the attractive forces that exist between molecules. And so starting off, we have London dispersion forces. All molecules have this force. It is the weakest intermolecular force. It's found in both polar and nonpolar molecules. And London dispersion comes as a result of temporary dipoles. And temporary dipoles are predominantly in between nonpolar molecules. So what is a dipole? A dipole is an uneven distribution of charge in a molecule. Temporary dipoles exist in all molecules because electrons are always moving, though some molecules may have a permanent dipole, which we'll get into later. And so nonpolar molecules are molecules where all of the dipoles within the molecule cancel each other out. This will result in a temporary dipole. So this is carbon dioxide. And so the oxygens are pulling electrons this way because they're more electronegative. And so they're pulling them away. Though they might be sharing with the carbon, they're pulling them this way because they're more electronegative. And so since they pull them in opposite directions, they'll cancel each other out and equal to zero. So this is a nonpolar molecule. And so this will result in a temporary dipole, which I'll further explain later. And so to determine whether a molecule is nonpolar or polar, you have to consider the shape, the atoms, and the bond dipoles. You can't only consider one of these three aspects. So it says the bond dipoles within the molecule are oriented in a way that they cancel out. So like here, you can see that they cancel out. The carbon is in the middle and the oxygens are pulling in different directions that they cancel it out. Same here for trigonoplanar. They pull in opposite directions from the boron molecule, and so they cancel each other out, and then it becomes nonpolar. And same with the rest of these. And then these are polar molecules. So you can't, since this was linear, you can't just assume, oh, because it's linear, that's also going to be nonpolar. No. The bond dipoles within these molecules do not cancel each other out. So since nitrogen is one more electronegative than hydrogen, and it also has 3 bonds. It's going to be a more electronegative, and it's going to pull the electrons towards it, rather than, it's not going to be equal like this molecule is not going to be equal. It's going to be way stronger this way. And even if they're pulling a little bit this way, this is going to be so much stronger that it will still have a bond dipole going this way. So the bond dipoles don't cancel out. And so the Lewis structure does not necessarily indicate the molecular geometry. So you can't just assume, oh, like this is the simple way that you would draw a water molecule. You might draw it this way. And you might assume, oh, since the oxygen is the most electronegative, there's going to be a pull from both directions in towards the middle, and then they'll cancel out. Nope. As I'll show later, this is a bent molecule, so the oxygen is really up here. And so the direction of the hydrogens towards the oxygen is actually going to be going upwards, and its vector direction will be up. So its bond dipole will not cancel out. And so this is a hydrogen molecule, and so this would be nonpolar. They would cancel each other out. The bond dipoles would cancel each other out, but it has a temporary dipole. So this is because of the electrons. So it has 2 electrons, and they're always moving. They're always constantly moving. And so for an instant moment, the electrons might be near this hydrogen. And so since electrons are negative, this is going to make this hydrogen negative and this one positive, since it doesn't have those electrons here. And then the next millisecond, it might switch over to this hydrogen, and it might become negative, and this one will become positive. So that just explains that there are temporary dipoles. And so how do London dispersion forces, how do they form? How are they created? So the temporary dipole in one atom or molecule induces another dipole in another atom or molecule. So this temporary dipole in this hydrogen might attract this positive end, might induce a temporary dipole in another molecule, and then their end might become negative, since these would attract. This end would become negative, and then another end would become positive, and that would thus create another dipole in another atom or molecule. And the neighboring atom or molecule gets attracted to one side of the molecule / atom, so then it has a dipole also, like I just explained. And the 2 atoms or molecules become attracted to each other, and London dispersion forces are created. So how strong of LD force is determined by its size, which in turn relates to its polarizability. So polarizability might be an intimidating word to you, and it was to me when I first heard it. And if you look up the definition, it might also be pretty intimidating and confusing. I'm going to simplify it for you. So polarizability is the smart definition, is how easy it is for the electron cloud to deform into a dipole. This might be kind of confusing. So simplifying a bit more, it refers to the interaction between the nucleus of an atom and its electrons. And simplifying it even more, in short, is how large the electron cloud is. It's really all it is. And so the higher the polarizability, the stronger the LD forces become. And so the strength of an LD force increases with increasing contact area, which is pretty much size, between molecules, and with increasing polarizability in molecules. So this is the main point, okay? As the number of electrons in a molecule increases, which also makes the electron cloud larger, the polarizability of the molecules increases. Furthermore, the larger molecules have stronger LD forces. So it's a direct relationship. As the number of electrons increases, the polarizability also increases. And then, therefore, the larger molecules, they have stronger LD forces. But you want to make sure, if you're asked a question on the AP test, you can't just say as the number of electrons in a molecule increases, the polarizability of molecules increases. You have to mention this electron cloud aspect. And so, which atom has, just an example, which atom has stronger LD forces, neon or krypton? So the krypton atoms have a larger electron cloud due to the number of electrons. So they have higher polarizability, thus they have higher LD forces. And see, I mentioned this larger electron cloud, and I would not put this in parentheses if you wrote it on a test. I would make that part of your answer. So moving on, we have polar molecules and their IMFs. And the essential idea for polar molecules is that the dipole moment of a polar molecule leads to additional interactions with other chemical species. So dipole moment is the key word, and polar molecule. So we'll explain what dipole moment means in a bit. So polar molecules, see these polar molecules dipole moment, which we'll explain, can induce three kinds of IMFs: dipole-induced dipole forces, dipole-dipole forces, and ion-dipole forces. So you might be familiar with the second one, and these first and thirds might be less familiar, but it'll all make sense in a bit. So what is a dipole moment? I keep on mentioning this word, what is it? So the dipole moment is essentially the difference in electronegativity between two elements. So for example, hydrogen's electronegativity is 2.2 and chlorine's electronegativity is 3.2. So you subtract them and their dipole moment is 1. And so the dipole moment not only has this magnitude, which is 1, but it also has a direction. So since chlorine is more electronegative, it'll be pulling the electrons more towards it, and so it'll become more negative, and it'll also have a direction going this way. And so starting off, there's dipole-induced dipole forces. So this occurs between a nonpolar molecule and a polar molecule. These forces are always attractive, and as the magnitude of the dipole moment of the polar molecule, so as we explained here, as the magnitude of the dipole moment of the polar molecule increases and the polarizability of the nonpolar molecule also increases, the strength of these forces increases. Makes sense, right? And this force is relatively weak. Next, moving on, we have dipole-dipole forces. So this force occurs between two polar molecules. These forces are always attractive, and the partially positive end of one polar molecule is attracted to the partially negative end of the other polar molecule. And because these are polar molecules, they have permanent dipoles. It's not temporary, it's permanent. And the strength of DD forces increases with increasing dipole moment. So to have DD forces, the molecule has to be a polar molecule, which is a molecule where all of the bond dipoles within the molecule do not cancel each other out. So instead of, for nonpolar molecule, the bond dipoles do cancel each other out. For polar molecule, it's the opposite. And so, like on this slide, you might think, oh, they cancel out, it's nonpolar. And I was explaining that bent molecule. And now you can see this is the correct Lewis structure. So you can see that there's this dipole moment going this way towards the oxygen, since there's more electronegativity from both hydrogens. It's going up this way. And then so the resultant vector dipole moment is going upwards. And this will become negative. This is attracting the electrons. These will become positive. And as you can see, these are bent. And it's a polar molecule because the bond dipoles don't cancel each other out. And the interactions between polar molecules are typically greater than those between, typically greater, than those between nonpolar molecules of comparable size. This is key, because these interactions act in addition to London dispersion forces. So like I explained before, all molecules have London dispersion forces. So then if they also have dipole forces, they're going to be stronger because they have more forces. And this comparable size aspect is very key. A question on the AP test might ask you, they might give you two molecules and one might be nonpolar and one might be polar. And then they'll give you the boiling points of both of them. And the nonpolar molecule might have a higher boiling point, And this may be because the nonpolar molecule is much, much larger than the polar molecule. And even though the polar molecule has dipole-dipole forces, the nonpolar molecule might be so large that it needs a higher boiling point to break those forces. And then last of the polar molecules with IMFs, this force occurs between, these are ion dipole forces, and this force occurs between a polar molecule and an ion. These forces are usually stronger than dipole-dipole forces, and they can become stronger in two ways. So the magnitude of the charge on the ion increases, and or they could both increase. Both of these things could happen, or only one could happen, and it would still become stronger. The dipole moment of the polar molecule increases. So either of these, they both can occur and become stronger, or only one maybe occurs, but it'll still become stronger. So how do they form? A positive ion, also called a cation, can attract the partially negative end of the polar molecule. And then a negative ion, or an anion, this is the second way, can attract the partially positive end of the polar molecule. So negative, positive, positive, negative. And then last, we have hydrogen bonding. So this is the strongest IMF. And this is a special case, these forces are a special case of dipole-dipole forces. And this refers to the dipole bond in the molecule between the partially positive hydrogen end being attracted to the partially negative end of another molecule, such as nitrogen, oxygen, or fluorine. This is very key. Hydrogen bonding can only occur when hydrogen bonds to nitrogen, oxygen, or fluorine. And I use the acronym NOF, it's pretty simple, nitrogen, oxygen, fluorine, to remember this. And these forces can occur between two different molecules or in different parts of one molecule. And I'll give you some examples. So first, these forces can occur between two different molecules. So this is ammonia and this is water. And so the partially positive end of the hydrogen is being attracted to the partially negative end of this molecule, this nitrogen. And that creates a hydrogen bond. This is one of the NOFs. It'll create intermolecular hydrogen bonding between two molecules. And again, these are just two water molecules. The partially positive end NOF, use the acronym NOF, oxygen is there, and it's partially negative end. So partially positive end attracts to the partially negative end. And again, these forces obviously can occur between two different molecules as shown here. And then these forces can occur in different parts of one molecule. So this is ethylene glycol, and this is one big molecule. And as you can see here, 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 and here, these are all hydrogen bonding. And as you can see, NOF, oxygen is there, partially negative end attracts to the partially positive end of hydrogen, same for all of these, and that creates hydrogen bonding. And so the final note, just as we emphasized for hydrogen bonding, these interactions, such as line dispersion forces, dipole-dipole forces, ion dipole forces, hydrogen bonding forces, etc., can occur in different molecules or in different parts of one molecule. So it's just like we explained earlier, this can occur in these forces also. So last final note, this is from the College Board and Michael Faribault. Because of COVID-19, they created these great videos, which I'm so thankful for. They created these great videos, just really explaining the units. If some of the students might have missed some lessons, they did like almost all the units, and they did a really great job of explaining these units. So if you found this lesson confusing, or you just wanted a review on this lesson, I would really encourage you to watch this video. And it's about 39 minutes long just because it's the longest video. Some of the other units are very, very short, but this one is the longest one. So maybe grab some popcorn, a drink, and sit down if you want and watch this video. So this is my bibliography of all the sources that I used in this presentation. And I just wanted to give credit to the great videos, articles, images, all that stuff that I used in this presentation. So I'll see you guys next time. Thank you for joining me today.